Hi everyone, this is Dr. Masood Yusuf. Thank you for having me. The topic that we will cover under this video lecture will be time independent perturbation theory. Under this topic, we will cover the following contents. First of all, we will define what is perturbation theory and what is the need of the perturbation theory. There are some assumptions relating to this theory that will be covered under this lecture along with the theoretical framework. First order energy, first order perturbed state, and second order energy will be calculated. And lastly, the use of the perturbation theory to non-degenerate states will be discussed. So let's start. What is perturbation theory? Perturbation theory is developed to deal with small corrections to problems which we have solved exactly, such as harmonic oscillator and the hydrogen atom. Perturbation applied to a system is of two types. One is time dependent perturbation and the other one is time independent perturbation. In this video lecture, we will cover time independent perturbation. What is perturbation? Perturbation means small disturbance. Remember that the Hamiltonian of a system is nothing but the total energy of that system. Some external factors can always affect the energy of the system and its behavior. So we have already solved examples such as hydrogen atom for which exact solution is available. When such systems undergo a small disturbance which is called perturbation, then we introduce this theory to calculate the new state of the system which is under perturbation. Why to bother about perturbation theory? What is its need? It reveals to us universal principles which are very important and cannot be obtained from just numerical simulation. Perturbation theories, in many cases, the only theoretical technique that we have to handle various complex systems, quantum as well as classical systems. Let's go through the assumptions relating to this theory. Number one, all eigenstates of unperturbed Hamiltonian H0 are known, as well as their corresponding eigen energies. So we have a system which is the pure system which is not affected by any external disturbance. We call that system as unperturbed system, and the Hamiltonian belonging to that unperturbed pure or original system, let's say, is H0. So all eigenstates relating to the unperturbed system, let's say those are N0 in the ket form, they are known along with their corresponding eigenenergies. You can see here En naught. N naught forms a complete basis in which any eigenfunction of the full Hamiltonian can be expanded. So let's discuss something about complete basis. This completeness of the basis mean simply that you can reach all possible directions in the Hilbert space. It means that any wave function can be made up from the basis vectors. In quantum mechanics, Hilbert space plays an important role. For these spaces, pure quantum states of the mechanical systems, they live in these spaces. As you know that in Cartesian we have I, j and k as basis vectors, and we can construct any vectors using the linear combination of those I, j and k basis vectors. So similarly, from the basis n naught, they form a complete basis, and any eigenfunction can be constructed using these eigenfunctions n naught. Perturbation, small disturbance, let's say it is h1 is known. This means that we can write down h1 using the complete basis of n naught. This is the meaning that how we define the perturbation h1, that we can write down h1 using the complete basis of n naught. That is, we know the value of expectation value of h1 for any n and m vectors. Quantum states with discrete eigenenergies are considered only. So we know that in quantum mechanics we have discrete eigenenergies. We do not consider any continuous eigenenergies. So these are the assumptions. Theoretical framework of the perturbation theory. The basic idea of perturbation theory is very simple. We split the Hamiltonian into a piece we know how to solve, that is the reference or unperturbed Hamiltonian, and a piece we don't know how to solve, which is the disturbance or the perturbation. Let's move on further. Let's consider a Hamiltonian. So we have discussed this basic idea of the theoretical framework relating to the perturbation theory, and now we discuss in detail about this basic idea. Let's consider a Hamiltonian H of a perturbed system, which is slightly different from the Hamiltonian H naught of unperturbed original system. So what we have H naught, which is the Hamiltonian of the original pure or unperturbed system. Due to some external effect, there is some disturbance, and that disturbance is in the form of Hamiltonian. It is affecting the original Hamiltonian of the system as H1. So we have a new system that has a perturbed system that has Hamiltonian, which is composed of Hamiltonian of the unperturbed system plus the Hamiltonian of the disturbance perturbation. The Hamiltonian of the perturbed system or the new system is H, which is equal to H naught plus H1, where H1 is small perturbation to original Hamiltonian. Let's assume the perturbed energy levels and the associated quantum states can be treated as superposition of terms in a kind of series solution to the full problem, such that energy of the perturbed system is. So we assume that the energy of the perturbed system, which is belonging to the system having Hamiltonian H, is composed of En naught plus En1 plus En2 and so on, where En naught, En1 and En naught, En2 are energy of the perturbed system. This is the energy of the perturbed system. This is the energy of the unperturbed system. This is the first order correction, and this is the second order corrections in the energy. So in short, energy of the perturbed system En is sum of the energies of the unperturbed system plus corrections such as first, second, third, and so on. Similarly, on a similar account, quantum state of the perturbed system is this, where n is the quantum state or the eigenfunction of the perturbed system, which is composed of the quantum state of the unperturbed system, and the first order corrections, first and second order correction, and so on, third or fourth and so on, orders of correction in quantum states. So we have the energy of the Hamiltonian of the perturbed system, energy of the perturbed system, and eigenfunction of the perturbed system. Now let's consider Schrödinger equation for the perturbed system, which is simply H n in the form of cat equal to En and n quantum state. This is the simple Schrödinger equation. Let's put the value of H, n, En and n from the previous equations, as you can see. So we have this equation 1. We have simply insert the values that we have derived. So we have this relation, which is 1. You can see this. So now we can pick this H naught and we can multiply with all the available states. Similarly, we have to multiply H1. If we open up these bracket, we have to multiply this H1 with all these states. Similarly, one by one we have to multiply En naught with all these states, En1, En2 with all these states, and we have a number of quantities. We have many quantities. What we are doing from this equation 1, we are collecting like power terms in equation 1. What does it mean? For example, for zero order means you have to look on to the superscripts. So H naught, N naught will be equal to En naught, N naught. So this H naught will be multiplied with this n naught state. So we have to add the superscript. We have the to add whatever is in the superscript. So 0 plus 0 will be 0. This is the only term on the left hand side which is of 0 order, and on the right hand side we have only en naught multiplied by n naught state. This is the only term that we have of 0 order on the right hand side. So for 0th order we have h naught n naught equal to en naught n naught. For the first order, so again we have to go back to the equation 1. H naught will also be multiplied with this n1. H naught will also be multiply with this n2 state. So 0 plus 1, so this makes the term of order 1. And when we multiply h naught with n naught, we have a term that has the order 2. So we are collecting only terms having order 1. So we have h naught n1, and in this when we multiply h1 with these terms, we have only h1 n naught. So you can see on the left hand side we have collected those terms, only those terms that has the order 1. And on the other side we have en naught n1, this is the term, and en1 multiplied by n naught. So only these two terms are available that makes of order 1. Similarly, for second order we have to collect only those terms that makes of order 2. For example, this h naught n2 and h1 n1, they are making of order 2. Similarly, on the right hand side we have en naught n1 and en1 n1. So also we have en2 n naught. We have 3 terms on the right hand side that are of order 2. So this is the equation 4. So for 0th order we have equation 2, first order, and for second order we have equation 3 and 4 respectively, and so on. So how we are utilizing these equations? Let's proceed further. Calculating first order energy. So what we are doing, multiplying both sides of first order equation. So for first order energy, what we are using? We are using this equation 3. We are not utilizing equation 2 because for equation 2 we know everything, because in assumptions we have already mentioned that h naught is known, n naught is known. So everything about the original pure unperturbed system is known. So for first order energy, how to en1, we need to know what is this energy. We need to know what is first order quantum state. So for first order we are using equation 3. We are taking equation 3 and multiplying with the known state n naught. So you can see that we are multiplying both sides with n naught. So this is n naught, this is the first order left hand side, N naught again first order right hand side. So when this N naught state will multiply this, we have this situation. So N naught simply multiplying with this. As we know, En naught and En1 is not an operator. So they are simply numbers. So we can pull them out of this in a product. So what we have? So here in left hand side, when H naught operator H naught will act on the bra state N naught, H naught will only act on N naught because this is the operator relating to N naught. It cannot act on N1. So when H naught will act on N naught, it will yield energy En naught according to the Schrodinger equation along with the bra N naught. So this is we have this one. And for this H1, this cannot act on N naught. So either on N naught bra and cat, we have we write it again as it is. And En naught and En1, they are constants, we can pull them out. So this is we have N naught N1, this product will yield 0 because as per the definition of orthonormal basis, when we have dissimilar states, their product will be 0, and when we have same states, we have the result 1. So what we have left on the right hand side, only En1 you can see here. Again this one is 0 because they are dissimilar states. The resultant is 0. So we have left with this. So we have calculated first order energy En1, which is our desired result. Perturbed energy is the expectation. What is this? Is the expectation value of the perturbed Hamiltonian H1 in the unperturbed state N naught. So this is the simply the expectation value of the perturbed Hamiltonian H1 in the states N naught. Let's calculate now first order perturbed state. In order to calculate this, let's multiply both sides of first order equation. Again we take the first order equation and now we multiply a different unperturbed state M naught. A system can have more than one unperturbed state. In previous calculation we have utilized the same state N naught, and now we are using a different unperturbed state. Let's say it's M naught. So again this is the first order equation. You can see multiplied with the unperturbed state M naught. So M naught, we have two terms on the left hand side and two terms on the right hand side. Again this H naught can only act on M naught. It cannot act on N1. We have this Em naught, and this H1 cannot act on either M naught and N naught states, so it remains as it is. En naught and En1, they are constants, so we can pull them out. So we have these M naught, N naught, they are now different, and they are unperturbed but different states, so their product is 0. So we have this result as 0. As M naught N naught are different unperturbed states, degenerate states, and are orthogonal to each other, so above equation become, so we put the values in equation 6, so we have this result. So what we have done, we have this result is 0. Let's take this to other side, and then we take the common M naught N1 product. So what we have this result. So from this result we can separate M naught N1 product. We have this result, which is the equation 7. So in equation 7, what we are doing, we have M naught N product. How we can define this or discuss this or express this equation 7 is that M naught N1 shows how much of the unperturbed eigenstate M naught is in the perturbed state N1. Additionally, it is proportional to the inner product of the perturbation between unperturbed states. The term in the denominator is called energy denominator. This term in the denominator is called energy denominator, which is the difference in energy between the two unperturbed states. So we can write this in this way also. The first order quantum state with the identity. Identity is the superposition of all the basis states of the ket times the bra. So we can in term for identity we can write this as ket times bra, and then from equation 7 we have calculated M naught N1 product. So we can put M naught N1 product value here from equation 7. So what we have, N1 as this is the result. This gives the new state under perturbation. So this was our goal. First we have calculated first order energy, and now we have calculated first order quantum state, which is the equation 8. So same can be done for second order energy and for second order quantum state N2. So but for second order case we are only calculating second order energy just to give you some idea, but the line of action is the same. We have calculated first order energy and then first order perturbation state. Similarly we can go on. So for second order we are just calculating second order energy just to save some time. So for second order we need to collect the second order equation. So where is the second order equation? This is the second order equation. 2 terms on the left hand side and 3 terms on the right hand side. So for second order energy, pick the second order equation, then multiply similar line of action as we have calculated for the first order energy, multiply with the state N naught. So this is N naught and this is N naught, multiply it, and then we have we know that En naught, En1 and En2, they are just constants. We can pull them out. So here on the right hand side we have this situation, and H naught can act on N naught. It will yield En naught, and this remain as it is, as H1 cannot act on this. So N naught and N1, they will be 0 as per the definition, as per the requirement we have utilized orthonormal basis. N1 is the superposition of only states that exclude the unperturbed states, and also N naught N1 is equal to 1. So for dissimilar we have 0, and for similar we have 1. So this equation, this last equation, will become, after inserting these values, En2 is equal to this. So we have only left En2, this becomes 0, this becomes 0, and on this side this becomes 0, we have only this. So only two, so En2 is available on the right hand side and this on the left hand side. So we have this. We have already so which is the, what is this? It is the expectation value of H1 between the states N0 and N1. Putting the values of perturbed state from equation 8 in the above equation. So we have already calculated N1. So where is, this is the equation 8. So to build second order energy, we will utilize the perturbed state value from the first order calculation. So inserting this value, we will reach to this. So we can take the summation like this, and this one and this one, these two terms in the numerator, so are complex conjugate of one another and can be simplified as square of the magnitude. So this is the final result of the perturbed second order energy. So we have reached our goal. So in the so we can also calculate second order state in the same way we have calculated first order energy. So that's all. So now we will move on to the example relating to the perturbation theory. So we will utilize perturbation theory to non-degenerate states. For this, we have used the book Quantum Mechanics, Theory and Applications. Let's quickly go through this example, which is about the utilization of perturbation theory to non-degenerate states. In order to illustrate the use of perturbation theory to non-degenerate states, we consider a perturbation of the form half p x square to the linear harmonic oscillator problem. So as we are familiar with the linear harmonic oscillator, which is the quantum mechanical analog of the classical harmonic oscillator, a particle subjected to a linear restoring force, the so-called harmonic oscillator. The diatomic molecule is an example of linear harmonic oscillator, provided that the interatomic force is an elastic one. So that's why we have considered the perturbation in the form of half p x square. Harmonic oscillator Hamiltonian is symmetric in momentum and position, and equation 28 is the Hamiltonian belonging to the harmonic oscillator. So this is the Hamiltonian belonging to the unperturbed harmonic oscillator. This is the perturbation H dash, written as half p x square. The eigenvalues and eigenfunctions of H naught are well known, and it is the we have already studied this about this in assumptions of the perturbation theory also. So H naught un en un is the Schrödinger equation belonging to the unperturbed linear harmonic oscillator. So we have this in this equation 30. We can define En as this, un wave function as this, omega as this. So one need to go through the theory of harmonic oscillator in order to understand these terms. For example, omega is the angular velocity, mu is the reduced mass, usually m1 m2 over m1 plus m2, and k is the force constant. So you need to revise your already studied topic relating to harmonic oscillator. This is the psi. So notice that the exact solution can easily be obtained. All that one has to do is replace k plus b. Thus, if we write h psi n equal to wn psi n, where h, so this is the system, this is the Schrödinger equation belonging to the system when perturbation is introduced, and the Hamiltonian is of course the sum of Hamiltonian belonging to unperturbed system, and this is the perturbation h dash. So we have this Wn as eigenvalues in the form of equation 36, or in this form as equation 37. So eigenvalue of the unperturbed system and the first order and second order corrections are given in equation 39 and 40 respectively. Notice that Wn1 is linear, whereas Wn2 is quadratic in B. Let us now employ perturbation theory to calculate Wn1 and Wn2. So let's apply perturbation theory and come out the value of Wn1 and Wn2, and then we match those values with equation 39 and 40, which are already calculated. So for Wn1 we have this, utilizing states of the unperturbed system, un are the quantum states of the unperturbed linear harmonic oscillator system. So this is how we calculate eigenvalue in the form of expectation value. So we have this result 41. So how we reach this? You need to go to the results derived in the solution 12.4. In the same book, you need to go to the chapter 12 section 4. So then you will know about the equation 41, and 41 is exactly the same as equation 39. So the calculation with the help of perturbation theory gives the exact result. And for Wn2 we have we have utilized two different states as we have done in perturbation theory that we have studied before this example. So we yield this. Again, you need to go to the section 12.4 of this book, and this is the same as equation 40. So by the implementation of perturbation theory we reach the same result. So that's all about the perturbation theory and one of its utilization. Thank you for having me.